Welcome again to NephroTube online nephrology lectures. This is our fifth lecture discussing conventional hemodialysis. We are discussing the different chapters of the book NephroTube Synopsis of Conventional Hemodialysis. Now we'll go through dialyzers overview. In the description of this video in YouTube, below the video, we'll find some important links. The first link is a link to this same lecture, but in Arabic language, for those who like to watch the lecture in Arabic. We'll find also a link to the playlist of video lectures about this book. You will find the link for the English playlist and Arabic playlist. We'll find link to download this book for free. You'll find link to download the PDF of this lecture for free if you like to use it. You will find a link for my website NephroTube, nephrotube.com, where you will find more lectures about nephrology than hemodialysis lectures. And finally, you will find a link to NephroTube social media accounts, the WhatsApp group, the Telegram channel, the Facebook group. You can join us to be always updated by the activities of NephroTube. And finally, it's better to subscribe to our channel and to make the notifications on from our channel, so you will be notified once we upload new lectures. As we mentioned in the first lecture, where we were discussing physiological principles of hemodialysis, we showed this figure. This figure is from chapter 1. We showed that the dialyzer has a semi-permeable membrane separating the two compartments, the blood compartment and the dialysate compartment, and the molecules and also the water are transported between the blood and the dialysate compartment through this semi-permeable membrane. So now we'll talk about the dialyzer in more details. First of all, I want to mention that mainly there are two types of dialyzers. The parallel plate dialyzer, but this was historically used. It is not used nowadays. The dialyzer that is used nowadays is called the hollow fiber dialyzer or the capillary dialyzer, and this is the one that we are discussing in this chapter in details. This is my talk outline. It is a long talk outline, but we will go through it step by step. First of all, what is the structure of the dialyzer? Each dialyzer has an arterial blood port or blood inlet, where the blood comes from the patient and then it flows into the dialyzer. Then we have the venous blood port or the blood outlet, where the blood passes from the dialyzer back to the patient. As we mentioned, parallel to the blood, there is the dialysate flow. So we have here the dialysate inlet port and here the dialysate outlet port. This part is called the header space. We have an arterial header space and the venous header space. The arterial header space is near the arterial blood inlet, and the venous header space is near to the venous blood port. Clotting of the dialyzer is common during hemodialysis sessions, but the most common site of clotting is the header space, which is the space between the header and the fibers. So these spaces are very common to be clotted during hemodialysis. We have here the potting material, and this potting material separates the blood from the dialysate, separates the red part from the blue part. These are the capillary hollow fibers. Each dialyzer has an average of 10,000 capillary fibers, which are semi-permeable, as we mentioned before. Inside these capillary fibers, you will find the blood, and we call the internal part of the capillary fibers, the blood compartment, and outside it we have the dialysate compartment where the dialysate flow. If we take a transverse section through this dialyzer and look through the dialyzer from upward, you will find here these are the capillary fibers, capillary hollow fibers, with the blood compartment inside and the dialysate, which has the blue color outside these hollow fibers. The next step, or the next point that we want to talk about, is the flow direction of blood and dialysate within the dialyzer. They are flowing in parallel counter current direction. They are flowing in opposite direction to each other. As I'm showing here, this is the blood inlet and the blood outlet, and the dialysate inlet is from the bottom and the outlet from the top. So the dialysate and the arterial and the blood are passing in a counter current flow opposite each other. The main advantage of this counter current flow of the blood and dialysate that it will create an optimal concentration gradient for solutes and allows continuous diffusion of these solutes, because if they are moving in the same direction, this may cause a point of equilibrium secondary to diffusion. But if they are passing in opposite direction, this guarantees that there is always a concentration difference between the blood compartment and the dialysate compartment. The next point to discuss is materials of the dialyzer membranes. Usually, the dialyzer membranes can be formed of one of the three categories: cellulose membrane, modified or substituted cellulose, and finally synthetic membranes. Let's start by each of them. These are examples of the cellulose membranes. Cellulose materials are less expensive than the modified cellulose and synthetic, but they are the least biocompatible. This is why they are not commonly used. They have low biocompatibility because cellulose membrane contains a free hydroxyl group, and this free hydroxyl group activates the immune system, complement and cytokines, which may cause adverse reactions and complications during dialysis session. That's why they tried to invent the modified or substituted cellulose. These are multiple examples. The most famous of them may be Hemofan. In the modified cellulose, it is more compatible than cellulose membrane, but less compatible than synthetic membrane. That's why we are saying here that it has intermediate compatibility. What is the modification they did for the cellulose to make it has better compatibility? They bound a free hydroxyl group to the material, to the cellulose, for example acetate. This decreases the antigenity of the cellulose membrane and makes it more compatible. Regarding the synthetic membranes, these are the examples. Synthetic membranes have the best biocompatibility, higher permeability, but they are more expensive. Some of these synthetic membranes are manufactured with a coating of antioxidant material such as vitamin E, so they may have less allergic reactions. And finally, some of these synthetic membranes also absorb middle molecules as beta-2 microglobulin, and we will talk about this point later on again, that some of the synthetic membranes may absorb some of the middle molecular weight molecules. Our coming point for discussion is the physical properties of the dialyzer. Regarding the dialyzer surface area, it usually ranges in adults from 0.8 to 2.5 meters square. There is no clear equation or criteria to how to choose the surface area to your patient. Usually, if you have a patient with large body, we use a large surface area membrane, and patients with a small body, we use a small surface area membrane. But there is a suggestion that the surface area of the dialyzer membrane could be roughly equivalent to the patient's body surface area, but this is not that much accurate. The other point of physical properties of the dialyzer is the dialyzer priming volume. We discussed a priming volume in the second lecture before of the extracorporeal circuit, and we mentioned that priming volume is the volume of the blood that can fill a cavity. So the cavity here is the dialyzer, and the volume of blood that can fill the dialyzer ranges from 60 to 120 ml, depends on the surface area of the dialyzer. The next point is the dialyzer sterilization. The most commonly used method for sterilization is the ethylene oxide, and we mentioned that too in the second lecture before, that also ethylene oxide is the most commonly used sterilization method for the blood tubing sets. So it is important, as we mentioned before in lecture 2, to eliminate ethylene oxide completely by rinsing before connecting the dialyzer for the patient, because if ethylene oxide reaches the patient, it may cause allergic reaction, and we call this type A dialyzer reaction. That will be discussed later in lecture 8 when we are discussing the complications of hemodialysis. Finally, if the patient is sensitive to ethylene oxide, so you have to use other methods of sterilization than ethylene oxide, as gamma radiation, steam autoclaving, and electron beam. The next point related to dialyzers overview is the dialyzer use. We all know that there is rising cost of dialysis supplies in absence of reuse. But and also we know, and we mentioned in the lecture where we were talking about the dialysis water unit, about the green nephrology and the impact of dialysis on the environment. So without dialyzer reuse, there is environmental impact of the contaminated wastes. Although of this, there is now a shift from reuse to no reuse. Although of the benefits, theoretical benefits of reuse, the shift now is to not use the reuse. In my book, I mentioned the reuse technique in page 44 and how to check the dialyzer before reusing it in our patients. I will not go through these details in the lecture. You can check them from the book. The next point, and I think this is the most important point that most of you are waiting, is the dialyzer efficiency and flux. Before going through what is dialyzer efficiency and what is dialyzer flux, I want to show you first the classification of solutes or molecules according to molecular weight. Small molecules or small solutes with molecular weight less than 500 Dalton, middle molecules with molecular weight between 500 and 15,000 Dalton, and large molecules or large solutes with molecular weight more than 15,000 Dalton. Small molecules as urea, creatine, phosphate, and other electrolytes. Middle molecules, the most important for us till now is beta-2 microglobulin. Large molecules as albumin and light chains and myoglobin. There may be a type writing error in the book edition you have. Check the molecular weight of creatinine in the edition you have. If it is written as 133 Dalton, please correct it 113 Dalton, and I'm sorry about this third or fourth type writing error in the book. The correct molecular weight of creatinine is 113 Dalton. Again, before going in the details of efficiency and the flux, especially before going the details of dialyzer efficiency, I want to talk about what is called extraction ratio. Extraction ratio is the percentage reduction of a solute across the dialyzer. And it is calculated as inlet concentration minus outlet concentration divided by inlet concentration. Let's take a real example to show exactly what is extraction ratio. Let's suppose that the blood inflow through the dialyzer has urea at a concentration of 100 mg per deciliter, and after the dialyzer after the diffusion within the dialyzer, the blood urea concentration at the outlet blood is decreased to 40 mg per deciliter. Then now the extraction ratio is the percentage reduction of urea between outlet and inlet. So if we calculate the extraction ratio here, the inlet concentration is 100, the outlet concentration is 40, and the inlet concentration is 100. So the extraction ratio here is 60%. This means that the urea at the blood outlet is decreased by 60% than the urea at the blood inlet. Now we can go safely through the dialyzer efficiency and dialyzer flux, and I will start by the dialyzer efficiency. Important point before going how to measure dialyzer efficiency, I want to mention what is dialyzer efficiency, or what dialyzer efficiency is denoting. Dialyzer efficiency denotes the ability of the dialyzer to remove small solutes by diffusion. And we mentioned that small solutes are solutes with molecular weight less than 500 Dalton, as urea, creatinine, phosphate, and other electrolytes. So dialyzer efficiency is related to removal of small molecules by diffusion. How to test the dialyzer efficiency? Actually, it can be tested or measured by two ways, which are the dialyzer clearance and the mass transfer area coefficient. But the most accurate is to be used is the mass transfer area coefficient, but we will discuss both of them. We will start by dialyzer clearance. What is dialyzer clearance? It is the volume of blood from which a solute is removed in a given unit of time. Again, I wrote here solute in a black, bold, and large size letters to stress on that dialyzer clearance is used for measuring of dialyzer efficiency, and dialyzer efficiency is related to removal of small solutes less than 500 Dalton. So what is meant by dialyzer clearance is the volume of blood from which a solute is removed. Let's take an example to make this definition more clear. The dialyzer clearance can be calculated by multiplying the QB, which is the blood flow rate, by the extraction ratio. The extraction ratio is the ratio we mentioned in the previous slides. Let's take a real example. If you have a urea with extraction ratio 7% at a blood flow rate of 200, so the dialyzer clearance will be 0.7, which is the extraction ratio, 70% will be 0.7, multiplied by 200, so it will be 140 ml per minute. So the dialyzer clearance is 140 ml per minute. What is meant by the dialyzer clearance is 140 ml per minute? It means that 140 ml of blood is cleared from urea per minute. This is the dialyzer clearance. And you will find the in vitro dialyzer clearance of the dialyzer you are using given by the manufacturer in the pamphlet of the dialyzer. And this is an example of one of the pamphlets of the dialyzer. This pamphlet you will find designed or supplied by the manufacturer in the box of the filter. For example, they mentioned here the dialyzer clearance of one of the filter of urea is 180, creatinine 165, etc. And they put these numbers. When the blood flow rate is 200, the dialysate flow is 500, and the ultrafiltration rate is 0. But an important point to mention that these in vitro dialyzer clearance supplied by the manufacturer are typically greater than the actual in vivo blood clearance level. So if we suppose that you will put your patient at blood flow rate 200 and dialysate flow of 500 and the ultrafiltration rate of 0, will not get these numbers. You will get a lower numbers of these in vitro dialyzer clearance supplied by the manufacturer. Now, what are the factors that can affect dialyzer clearance? First of all is the thickness of the membrane. Membranes which are of higher thickness, thicker membranes, have lower permeability and clearance than thinner membranes. However, thicker membranes can withstand high transmembrane pressure compared to thinner membranes, but they have a lower dialyzer clearance. The second point that can affect the dialyzer clearance is the density and size of the pores. For sure, if density is high of the pores and the size is wide pores, the clearance will be better. Then the surface area of the membrane. It is logic that if the dialyzer has a large surface area, so the clearance will increase and vice versa. And finally, the blood flow rate. We mentioned that dialyzer clearance equal blood flow rate multiplied by extraction ratio. So it is logic that when blood flow rate increases, the clearance will increase. These figures are used from chapter 6 that we will talk about later, about adequacy of hemodialysis. So as you see, the relation between blood flow rate and the clearance is increasing, is directly proportional, but it is not linear. If you see here, the line is not increasing in a linear shape. There is a sort of plateau at the end, and we will talk about this later in the chapter of adequacy of hemodialysis in lecture 6. Now we will go to the second method of assessment of dialyzer efficiency, which is more accurate, which is the mass transfer area coefficient. The mass transfer area coefficient is more accurate than the dialyzer clearance. What is the mass transfer area coefficient? Again, here I wrote the word solutes in a bold, large words to ensure that mass transfer coefficient area is used to measure the dialyzer efficiency, which denotes the ability of the dialyzer to remove small solutes. The mass transfer coefficient area, it is the solute's theoretical maximum dialyzer clearance, assuming that both the blood flow and the dialysate flow are limitless. So it is a theoretical number. The mass transfer area coefficient, which is abbreviated as KOA. KO is the permeability coefficient of the membrane. It indicates the permeability. So it can be affected mainly by the thickness of the membrane and the density and size of the pores. The thinner the membrane has the higher permeability coefficient and the higher mass transfer area coefficient. The same for density and size of the pores. The higher the size, the higher the density, and the wider the size of the pores will have a higher permeability. The A in the KOA abbreviation denotes the surface area, and this shows that surface area also can affect the mass transfer coefficient. According to the KOA, we classify our dialyzers into low efficiency dialyzer membrane and high efficiency dialyzer membranes. The low efficiency dialyzer membranes has a mass transfer coefficient area of urea less than 500, while higher efficiency dialyzer membranes has a mass transfer area coefficient of urea of more than 600. An important point that I want to finish talking about mass transfer coefficient area is the relation between the mass transfer coefficient area, blood flow rate, and dialyzer clearance. Here, there are two lines, one for a dialyzer with a KOA 1000 and one for a dialyzer with KOA 500. So this is a high efficient dialyzer and this is a low efficient dialyzer. In both dialyzers, you will find that with increasing the blood flow rate, the clearance will increase. But you have to know that at about blood flow rate of 200 or 100, dialyzers with mass transfer coefficient of 500 have nearly similar clearance for dialyzers with mass transfer coefficient of 1000. Look here at 100, there is no difference between the two dialyzers, although the one with the blue line has more efficiency than the one with the green line. Also, at 150, the difference between them is not that much. At 200, the same. So, while at, for example, at blood flow rate of 500 or 400, we'll find a huge difference between the clearance of both the dialyzers. This highlights that it is important that if you are using a dialyzer with high KOA, it is advised to deliver a high blood flow rate to get the most benefit of these dialyzers. But if you will use a very low blood flow rate, there is no difference by using a high efficient dialyzer and low efficient dialyzer. The next point to discuss is the dialyzer flux. The dialyzer flux denotes the ability of the dialyzer to remove water and middle molecules. Middle molecules between 500 and 15,000 Dalton. We mentioned before the classification of molecules, and the most important middle molecule here from 500 to 15,000 is the beta-2 microbillion. And for a sort of revision, again, we mentioned that dialyzer efficiency is the ability of the dialyzer to remove small solutes by diffusion. But now we are talking a dialyzer flux is the ability to remove water and middle molecules by the dialyzer. How to measure the dialyzer flux? First, by what is called the ultrafiltration coefficient. Okay, what is ultrafiltration coefficient? Ultrafiltration coefficient definition is the volume of water that can be transferred across the membrane for every 1 millimeter mercury difference of the transmembrane pressure in 1 hour. Okay, again, the ultrafiltration coefficient is the measure of the volume of water that can move from the blood compartment to the dialysate compartment across the semi-permeable membrane for each 1 millimeter mercury difference of the transmembrane pressure in 1 hour. So the ultrafiltration coefficient is related to water movement. And according to ultrafiltration coefficient, we divide our dialyzers into low flux dialyzers and high flux dialyzers. Low flux dialyzers have ultrafiltration coefficient, water permeability or water ultrafiltration less than 10 ml per hour per millimeter mercury, while high flux dialyzers have ultrafiltration coefficient, water permeability or ultrafiltration of more than 20 ml per hour per millimeter mercury. Ultrafiltration coefficient and water, which is equal to water permeability, can be affected by the membrane thickness and pore size. There are some important issues related to the use of high flux membranes. The first is that with high flux membranes, with wide pores, high flux membranes have wide pores and high density of pores, there may be overfiltration, over ultrafiltration with the use of these flux membrane dialyzers. So it is crucial to have machines that can preciously regulate the ultrafiltration rate. And actually, the hemodialysis machines that we are using now are preciously regulating the ultrafiltration rate. So the issue of over ultrafiltration is very difficult to happen nowadays with high flux membranes in our dialysis machines. But in the past, our professors told us that they were manually regulate the ultrafiltration in very old machines. So the issue of over ultrafiltration may occur in these old machines. But the nowadays used machines have a precious regulators for ultrafiltration rate, and the issue of this over ultrafiltration is difficult to happen. The next point that I want to mention here, related to the use of high flux membrane, the possibility of back filtration of back leak. As I'm showing in this figure, at the blood inlet here, the pressure in the blood compartment with the red line will be more than the dialyzer compartment. But with ultrafiltration of water throughout the dialyzer, from the blood compartment to the dialyzer compartment, at the outlet of the filter of the dialyzer, you will find that the pressure in the blood compartment will become lower because water is ultrafiltered from the blood compartment to the dialyzer compartment. So we'll find that the dialyzer compartment will be high. So at the end of the filter, as the dialyzer compartment is higher than the blood compartment, this may cause a possibility of back filtration or back leak of water from the dialysate to the blood compartment, secondary to increased pressure in the dialysate part. And this is important. Why? This is important because if you will use high flux membrane and there is a possibility of back filtration or back leak, so there is a possibility of a movement of water from dialysate to the blood, you have to use ultra pure dialysate that we mentioned in the previous lecture. Because if you use pure dialysate with higher level of colony forming units and endotoxin units, this will increase the possibility of inflammation and immune reaction in the body of the patient. So it is highly suggestible to use ultra pure dialysate if you use high flux membrane because of the possibility of back leak or back filtration. The last point or the last issue related to the use of high flux membrane or dialyzers is the membrane fouling. I mentioned before, while I was discussing the different types of membrane dialyzers, that the synthetic membrane and actually the high flux dialyzers are formed of synthetic membranes. And we mentioned that synthetic membranes can absorb some of proteins. If you remember, you'll find this in table 5.2 in my book. So if these membranes absorb proteins when they come in contact with blood, the protein absorption will lead to clogging and fouling of the membrane and reduce its performance. So we have to put this also in mind. So now again we are talking about dialyzer flux. We mentioned first we can assess the dialyzer flux by using the ultrafiltration coefficient. The next point to how assess the dialyzer flux is by using the beta-2 microglobulin clearance, pore size, and sieving coefficient. Let's see the numbers. We will compare now between low flux and high flux in different points. The first point is the ultrafiltration coefficient. We mentioned that in low flux, the ultrafiltration coefficient is less than 10, and we mentioned that the high flux, the ultrafiltration coefficient is more than 20. I mentioned here 10 to 50 for the ultrafiltration, and this is according to the Japanese classification, and I will show you now the Japanese classification of the dialyzers. But we can say that the ultrafiltration coefficient here is more than 20 as the international references, or 10 to 50 according to the Japanese classification. Regarding beta-2 microglobulin clearance, the low flux has beta-2 microglobulin clearance less than 10 and the high flux more than 20. It is the same in number as the ultrafiltration coefficient but with different units. Again, beta-2 microglobulin clearance may be more than 20, and it may be 10 to 50, as I will mention now, according to Japanese classification. Regarding the beta-2 microglobulin sieving coefficient, you will find the sieving coefficient mentioned on the high flux filters only. The beta-2 microglobulin sieving coefficient of high flux dialyzers is more than or equal 0.6. By the way, we mentioned in chapter 1, in first lecture, what is sieving coefficient exactly in details. But in short, the sieving coefficient is the difference in concentration of a molecule or solid between the dialysate and the blood compartment. You can check again first lecture for more details about sieving coefficient. Regarding membrane pore size, it is logic that the low flux dialyzer has a smaller or narrower membrane pore size, less than 1.8 nanometer, while the high flux dialyzers have a membrane pore size more than or equal 3.5 nanometer. And finally, the molecular weight cutoff. The low flux dialyzers can remove molecules up to 5,000 Dalton, while high flux dialyzers can move or can remove solutes or molecules with a molecular weight up to 25,000 Dalton. I want to show you also the Japanese classification of dialyzers, as in Japan they have the super high flux dialyzers that are commonly used there, and they are not used as much worldwide. The low flux dialyzer, type 1 dialyzer in Japan, with beta-2 microglobulin clearance less than 10. High flux type 2 from 10 to 30, and 3 from 30 to 50. That's why here I mentioned 10 to 50, and I want you also to know that beta-2 microglobulin may be 10 to 50 in high flux dialyzers according to Japanese classification. Super high flux dialyzers, type 4 and type 5. Type 4 from 50 to 70, and type 5 more than 70 ml per minute for beta-2 microglobulin clearance. Now, I want to talk about available evidence comparing the use of low flux and high flux membranes. Which is better? Actually, the available evidence going to that there is no much difference between high flux and low flux. But the available evidence has a lot of critical appraisal, and most of the experts suggest the use of high flux membrane. The two mega trials compared the low flux dialyzer and high flux dialyzers are the Hemo study and the MPO study. The Hemo study, which is the effect of dialysis dose and membrane flux in maintenance hemodialysis, they studied about 1,846 patients undergoing 3-time dialysis per week, and they divided them into patients who will use high flux dialyzers, and patients with low flux dialyzers, and the patients with high dialysis dose and patients with standard dose. They found that the primary outcome, which was death from any cause, and also secondary outcomes, were not significantly different between high flux and low flux groups, and also between the standard or high dialysis dose. But in the high flux group, there were significant reduction in the risk of death only from cardiac causes, and also the combined outcome of first hospitalization or death from cardiac causes. So, according to the study, high flux dialyzers may be beneficial for cardiac patients. Regarding the MBO study, which was the membrane permeability outcome study, it was a prospective randomized controlled trial investigating the use of high and low flux dialyzers in hemodialysis patients with low serum albumin below than or equal 4 and patient with normal serum albumin more than 4. They found that there is no difference in survival between high flux and low flux dialyzers in patients with normal serum albumin, but in patients with low serum albumin, there was better survival rates in patients using the high flux dialyzers. And finally, there was a post-hoc secondary analysis for the MPO study showed that the high flux membranes may improve survival also in diabetic patients. Now we talked about dialyzer efficiency and dialyzer flux. we need to make an interrelation between efficiency and flux. Is it always membranes with high efficiency have high flux and membranes with low efficiency have low flux? Typically, the high flux dialyzers usually have high efficiency and vice versa. And this is very common in the dialyzers we are using in adults. But actually, this is not always the situation, as there may be a small low efficiency dialyzer that is of high flux, and this may be used in children. I'm not a pediatric nephrology, but as mentioned in different references, that this can be used in children. And also there may be a high efficiency dialyzer, but that is of low flux. Now, after finishing the talk about dialyzer efficiency and flux, I want to go through a very important updated point, which is expanded hemodialysis using a medium cut-off membrane. We mentioned that low flux dialyzers have a molecular weight cutoff 5,000 Dalton. They can remove molecules with molecular weight up to 5,000 Dalton. High flux dialyzers can remove molecules up to 25,000 Daltons. Medium cutoff dialyzers here that are used for expanded hemodialysis can remove molecules with molecular weight up to 45,000 Dalton. High cutoff dialyzers can remove molecules up to 65,000 Dalton, and high cutoff dialyzers are the dialyzers that are usually used for treatment or making dialysis for patients of multiple myeloma to remove monoclonal free light chains. You can see this is 65,000 Dalton. This is near to the molecular weight of albumin, so it cannot be used in chronic hemodialysis. The high cutoff dialyzers cannot be used in chronic hemodialysis patients because it will cause large amount of albumin loss. That's why they invented the medium cutoff dialyzer with a molecular weight cutoff of 45,000 to be higher than or more than high flux, but lower than the high cutoff dialyzers, and to be used during routine hemodialysis, conventional hemodialysis, and they named the dialysis by medium cutoff dialyzers expanded hemodialysis. What are the benefits of the use of medium cutoff dialyzers and expanded hemodialysis? First, there is evidence that it reduces inflammatory mediators. It improves erythropoiesis stimulating resistance. It improves the physical components of quality of life. It improves uremic pruritus, and finally, it provides clinical benefits and better outcomes. Before going through the next point in the lecture, I want to mention an important point or a notification, because you can meet this while you are reading in the literature. Let's see. This is the low flux dialyzer, okay, in the Japanese classification. So it can remove molecules up to 5,000 Dalton. High flux dialyzers can move up to 25,000. So regarding super high flux, where I can put it in this diagram? According to the Japanese classification, super high flux dialyzers can remove molecules up to 30,000 Dalton or 35. So it is logic to put high flux dialyzers in this diagram here between the high flux and medium cut-off dialyzers, because it removes from 30 to 35,000 Dalton. But take care, some references also calling high cut-off dialyzers as super high flux. Why? These references are not using the Japanese classification. So if the reference you are reading is using or depending in their references on the Japanese classification, if they mention the super high flux, so they mean that the super high flux is removing molecules up to 30,000 Dalton. But in other references, you will find that they are not using or referencing to the Japanese classification, and they mention that these high cutoff membranes with molecular weight cutoff up to 65 are also called super high flux. So take care while you are reading. And by the way, there are third references that mention that high cutoff can remove up to 65, while super high flux can remove up to 60. So the terminology is different between different literature, so take care while you are reading the references. The next point that we will mention is the albumin and amino acid use during hemodialysis. Regarding the albumin and the amino acid loss, not use, albumin and the amino acid loss during hemodialysis. In conventional hemodialysis using low flux membranes, albumin leakage and loss is usually absent, while the using of high flux dialyzers during conventional hemodialysis, there will be albumin loss, but in very low proportion, less than 2.4 gram per 4-hour treatment. If you are using a high cutoff dialyzer, this is not in conventional hemodialysis. The high cutoff dialyzers only are used for management of multiple myeloma. But if you use the high cutoff dialyzers, the albumin loss ranges from or varied from 1 gram to 4 gram per 4-hour. Different references show different volumes of loss. Finally, the use of medium cutoff dialyzers, the newly invented medium cutoff dialyzers used in expanded hemodialysis, the albumin loss will be about 2 to 4 gram per session were reported. Regarding amino acid loss, it is suggested that about 6 to 8 gram of total amino acid can be lost during hemodialysis session, but a loss up to 12 gram also has been reported. Why it is important to know that there is albumin loss or amino acid loss during different hemodialysis therapies? This is important for the nutritional status of the patient, especially if the patient is malnourished. And this data is very important to your nutritionist to adjust the protein intake of your patient. Now we will go through the last point, which is the dialyzer monitoring and the related alarms. What are the alarms and monitors related to the dialyzer action? First is the transmembrane pressure monitoring. We mentioned in chapter 1, in lecture 1, we showed this figure that the transmembrane pressure means that the pressure in the blood is higher than the pressure in the dialysate, and the difference between them is called the transmembrane pressure. And it is important for water movement from the positive blood compartment to the negative dialysate compartment, and it is the main point related to ultrafiltration. You can refer back to lecture 1 for more details. So the transmembrane pressure is the difference in pressure between the blood compartment and the dialysate compartment. What is the accepted transmembrane pressure limit? Actually, you will find that each manufacturer provides information about the maximum TMP of this dialyzer in its brochure or pamphlet. So you can open the brochure or pamphlet of the dialyzer to know what is the maximum transmembrane pressure that can work with your dialyzer. But the European Renal Best Practice Guidelines suggest that the transmembrane pressure limit of positive 300 mm mercury may be a safe upper limit for all dialyzers. Okay, when the transmembrane pressure monitor can give you alarm if there is a change in transmembrane pressure, if it is increased or decreased. What may increase the transmembrane pressure? First, if the dialyzer is clotted. If the dialyzer is clotted, so some of the pores are clotted and the surface area of the pores decreased, and this will increase the resistance in front of the positive pressure of the blood compartment, which will cause more increase in the pressure of the blood compartment, and increasing the difference between the blood compartment pressure and the dialysate compartment pressure. The second point is, or the second point that may increase the transmembrane pressure, if you are using a small surface area dialyzer and you are targeting a high ultrafiltration ward. This is the same as if you have a large dialyzer that is clotted. So if you are using a small surface area dialyzer and you need a high ultrafiltration, this will make a resistance through the pores and will increase the pressure in the blood compartment. What may decrease the transmembrane pressure? We mentioned that the pressure in the dialysate is negative, is always negative. If there is any air in the dialysate compartment, this negativity will be lost. So in case of opening the dialysate compartment to the atmosphere, because the dialyzer lines are not attached well, so air may go through the dialyzer compartment, and the dialyzer compartment loses its negativity. So the difference between the blood compartment and the dialysate compartment will decrease, and you will have an alarm for low transmembrane pressure. The second alarm related to dialyzer monitoring is the blood leak detector. We talked about it in details in the last lecture in the dialysate circuit, but again rapidly, the blood leak detector is available or is present at the draining of the dialysate. If it detected any blood in the dialysate, this means that there is a rupture of the fibers of the dialyzer. And you can go back also to the previous lecture to check what we mentioned about false blood leak detector alarms. The next alarms that can be related to the dialyzer function is the pressure monitor. And also we mentioned that in details in lecture 2. But in short, if there is dialyzer clotting, we'll find an increase in the post-pump arterial pressure monitor and a decrease in venous pressure monitor. In lecture 2, we mentioned in details all factors that can affect post-pump, pre-pump arterial pressure monitor and venous pressure monitor. Whatever the pressure in these areas will increase and decrease or decrease. But if you have a clotted dialyzer, this pressure will increase, this pressure will decrease, and the transmembrane pressure that we mentioned in the previous slides will increase. My advice to you now after you watch this lecture is to go to your hemodialysis unit, get your dialyzers, filters, and check the data wrote on them, and get the pamphlet or the brochure from the box of these dialyzers and check the data present in them to apply this lecture. Now we finished this important lecture, and the next lecture we will go through hemodialysis dose and adequacy. We will talk in details about KT over V, different forms of KT over V, which one must be used in which situation, what are the normal or suggested recommended values of KT over V, and other issues related to hemodialysis adequacy and dose. See you in next lecture.